Yeah, so let us start with today's lecture. Today we're going to give a full classification of Möbius transformations up to conjugation. So up to conjugation in the Möbius group of C bar. We're going to show that, in particular, that every Möbius transformation is conjugate to some standard example, and we're going to decide when two standard examples are conjugate to each other or when not. Then we're going to recall the statement that Möbius transformations are conformal, and this is because they are holomorphic bijections of the Riemann sphere. And then using the classification up to conjugation, using the fact that every Möbius transformation is conjugate to a standard example, we're going to take the geometric picture we drew for the standard examples and then apply the inverse of the conjugating Möbius transformation to obtain a geometric picture for arbitrary Möbius transformations. We're going to start with one type of transformation, and then we're going to cover the rest of the types in the next lecture. So let's start with the classification up to conjugation. So in the last lecture, in the review, when showing that if two Möbius transformations have the same set of fixed points, then they commute. We use, and I left as an exercise, the statement of this lemma, which is, if I have a Möbius transformation with exactly one fixed point, and that fixed point is actually the point at infinity in C bar, then nu is a translation. And if the Möbius transformation has exactly two fixed points, and these two fixed points are 0 and infinity, then it must be the case that nu is multiplication by some non-zero complex number. So let's. I will leave you the first statement as an exercise. And I'm going to prove the second statement. So suppose that nu is mu of A, right? With A, let's say that it's a matrix alpha, beta, gamma, delta, GL to C. Right? So since nu fixes infinity, since nu of infinity is equal to infinity, what I can deduce about this matrix is that gamma is 0. Okay, and now since 0 is a fixed point, 0 is equal to nu of 0, which is alpha 0 plus beta divided by delta. Right? I mean, here as a side note, notice since I already know that gamma is 0, I also know that delta cannot be 0 because A is invertible. Right? But so now what I know is that beta is 0, right? So what I know is that A is equal to alpha 0, 0 delta. So nu of Z is equal to multiplication by alpha divided by delta. So there it is, so that you can see what I wrote. Okay, so this is the lemma, and Right. So so how do we use this lemma? Well, just like we did in the previous result, the one that relates the commutativity of two Möbius transformations with the relation between their sets of fixed points. Namely, what we are going to do is that by now we know that an arbitrary Möbius transformation has either an arbitrary Möbius transformation different from the identity has either exactly one fixed point or exactly two. So and then we can always take a Möbius transformation that puts that sends the fixed point or fixed points to convenient locations, namely to infinity if there's only one fixed point, or to 0 and infinity if the fixed points are 2. Right? So what we're going to do is we are going to take our arbitrary Möbius transformation. We're going to take another Möbius transformation that sends the fixed points to convenient locations. We're going to conjugate the original Möbius transformation with this convenient, with this other convenient transformation, and we're going to be able to deduce that the conjugation, let's say nu tau nu inverse, let's say, is either a translation or multiplication by some non-zero complex number, so that for this conjugation, nu tau nu inverse, we know that it's a standard example, right? And then later we're going to use the inverse of the conjugating transformation to map back the geometric picture we had for the standard examples. So this is the theorem that every Möbius transformation is conjugate to a standard example. And you see, well, we know that an arbitrary Möbius transformation has one or two fixed points. So here the original the starting point is nu, not tau, as I said a few moments ago. So it's nu, and then I know that nu has either one or two fixed points, and kind of I split the analysis into the two possible cases, right? Exactly one fixed point or exactly two fixed points. And here further, the case of exactly two fixed points, I divided into two cases, whether infinity is a fixed point or not, right? Now, here what I do is I explicitly compute some matrix that with the property that when I conjugate, I have the fixed point conveniently located, or here an explicit matrix that when I conjugate, it has the conjugation has convenient fixed points here and here. But other than that, the strategy is the one I said. That is, one conjugates the given transformation nu with a Möbius transformation that sends the fixed point to a convenient location, right? And then one deduces, in this case, that this conjugation is a translation. So nu is conjugate to a standard example, and here the strategy is the same. And also in this other subcase, namely, I take a Möbius transformation that sends the fixed points to convenient locations. And then I see, okay, the conjugation has this fixed point, so it's multiplication by a non-zero scalar. And so nu is conjugate to a standard example. Right? So the strategy should be clear, and the rest, the rest is occupied, is devoted to providing an explicit matrices that do the job. That's all. All right, so now we know that every Möbius transformation is conjugated to a standard example. The two crucial points were, well, one, the number of fixed points of a Möbius transformation different from the identity is either 1 or 2, right? Exactly 1 fixed point or exactly 2 fixed points. That's first crucial fact. Second crucial fact, a Möbius transformation that fixes only that has 1 fixed point and the fixed point is infinity is a translation. And if a Möbius transformation has exactly 2 fixed points and these 2 points are 0 and infinity, then it's multiplication by a non-zero complex number. Right? So those are the two crucial facts for the proof that every Möbius transformation is conjugated to a standard example. And now, if we want to achieve a full classification, then the question becomes, okay, now take two arbitrary standard examples. Are they conjugate or not? Or more accurately, can we classify all standard examples up to conjugation? So can we give a criterion so that if you give me 2 standard examples, then I can decide whether they are conjugate or not in the group of Möbius transformations of C bar? Unfortunately, the answer is yes. So the first observation is that the number of fixed points is invariant under conjugation thanks to our identity that we have been using repeatedly. So the first thing we can say is that a Möbius transformation with exactly 2 fixed points is never conjugate to a Möbius transformation with exactly 1 fixed point. Right? So multiplication by a non-zero complex number different from 1 is never conjugate to a translation by a non-zero vector, for instance. So we can already start distinguishing the two cases, right? We can focus on first classifying all translations up to conjugation in the Möbius group, and second, we can focus on classifying all the functions of the form multiplying by some non-zero complex number up to conjugation in the Möbius group. And the classification is really this one. Translations are always conjugate. And if you give me 2 non-zero scalars different from 1, let's say alpha and alpha prime, multiplication by alpha and multiplication by alpha prime are conjugate in the Möbius group if and only if one is the other or its inverse. That's what the second statement says. So the proofs can be achieved at the matrix level, pretty much. So let's see the first statement. So you see, when I conjugate this matrix, a matrix giving rise to a translation, if I conjugate it by you see, just by this matrix, one can just perform the computation, and what I see is that this conjugation has the effect on this matrix of multiplying this corner with lambda. So this means that conjugation allows me to to rescale the upper corner, right? Freely. So in order to obtain beta prime, I only need to take lambda appropriately, right? Namely, lambda equal to beta prime divided by beta. So these matrices are conjugate in just as matrices in SL2C. So when I take Möbius transformations, I have mu of this equal to mu of this, but the one on the left is equal to mu, right? Because mu of A times B is equal to mu of A preceded by mu of B. All right, for the second statement, well, it is clear that this matrix is conjugate to itself, right? But also by permuting the diagonal entries, and by noticing that permutation of diagonal entries can be achieved by conjugating by this other matrix, I see that alpha 0, 0, 1 is conjugate as a matrix to 1, 0, 0 alpha. Well, and the rest I just take the corresponding Möbius transformations, right? And realize that you see this Möbius transformation is the Möbius transformation associated to this matrix is precisely multiplication by 1 divided by alpha. Right? That is, I have this equality, right? So mu of multiplying by alpha, multiplication by alpha is conjugate to multiplication by 1 over alpha, 1 divided by alpha. So this shows that if I have this equality, then these two are conjugate. Yeah, and now I have to show that if they are conjugate, then the alphas are related by one is the other or its inverse. And so let's assume that that these two Möbius transformations are conjugate, and that the conjugation is given by the Möbius transformation associated to some matrix, right? Some matrix B. All right. Now notice this. So since I'm conjugating, what I can say is that mu B of the fixed points of this one are the fixed points of this one. That is, are the fixed points of this one. So mu B of fixed points of these ones, which are 0 and infinity, is equal to fixed points of this one, which are 0 and infinity. That's exactly what I'm saying here. Right? So the set 0 infinity is preserved by mu of B. And then I have two cases, right? Either mu B fixes 0, and hence also infinity, or it sends 0 to infinity, and hence infinity to 0. And then I'm going to analyze the two cases. In one of the cases is going to tell me alpha and alpha prime are equal. The other case is going to tell me alpha prime is equal to alpha inverse. So suppose that mu of B fixes 0. Right? Then mu of infinity, mu B of infinity is infinity, right? And then from that, what I deduce by seeing at the matrix is that I have 0 here and 0 here, right? This one is because it fixes infinity, and once I know that, since it fixes 0, then I know that this is 0. Okay, and so using that information, when I just take this matrix and conjugate it with B, in which I know that this happens, it's going to give me back this matrix itself. So that on the one hand, and on the other hand, you see when I take the Möbius transformation of this one, it gives me the Möbius transformation of this other matrix with the prime. And how can I recover the prime? Well, I can recover by evaluating this Möbius transformation at 1, the complex number 1. So that's what I do. Alpha prime can be recovered that way. But this Möbius transformation is equal to this, so I substitute. Right? But this Möbius transformation is the Möbius transformation of the product, where here, of course, be inverse. Right? And this is because taking Möbius transformation is a group homomorphism. Right? But this matrix gives me precisely the matrix without the prime. And when I evaluate that at 1, I recover alpha. And so alpha prime is equal to alpha. In the other situation, namely when mu of b sends 0 to infinity, well, it also sends infinity to 0. And so in that case, then what I can deduce is that the diagonal entries are 0. And then knowing that those diagonal entries are 0, when I perform this matrix product, I see that it simply permutes the diagonal entries here. But so this is the same alpha, right? And then I play the same game as before, namely. Alpha prime can be recovered by evaluating this Möbius transformation at 1. This Möbius transformation is equal to this conjugation by hypothesis. But computing this composition of Möbius transformations is equal to the Möbius transformation of the product. And then, this product just interchanges the diagonal entries. And when I evaluate this at 1, it's 1 divided by alpha. So it's alpha inverse. So alpha prime is alpha inverse. Okay, so what have we proved? We have proved that any two Möbius transformations with exactly one fixed points are conjugate, and they are all conjugate to any translation by a non-zero vector. Right? So all Möbius transformations with exactly one fixed point, they all form a single conjugacy class in the Möbius group. And the ones that have exactly two fixed points, the conjugacy classes are parametrized by pairs of mutually inverse non-zero complex numbers, different from 1. Right? So somehow here the picture here is something like you have the complex plane, let's say, right? And then you have the origin and you have 1. Okay, so this is 0, this is 1, and you have the let's say the unit circle. Oops. Right, and somehow you see, for instance, if you say, okay, I'm going to take only as representatives of these pairs only half, you can say, okay, take the alphas here, because the alphas here, and let's say in half the circle, because then you know that the inverses are going to be precisely the other ones, right? For instance. So my point is that it is not so hard to visualize how the set of all these pairs looks like, right? It looks like as identifying here any point with its inverse. Right? So kind of any point with its inverse, any point with its inverse, etc. Now, remember that when we studied the functions given by multiplication by some non-zero complex number, different from 1, we distinguished 3 cases. I mean, namely, when when the complex number lie on the unit circle, when it was a positive real number, and when it was kind of in the rest, right? Kind of when it was a complex number, not in the unit circle and not a positive real number. Right? So we carry on that distinction between these three cases to the general case, and then we make this definition. A Möbius transformation, different from the identity, is said to be parabolic if it has exactly one fixed point, and if it has exactly two fixed points, we say that it is elliptic if it is conjugate to multiplication by some element of the unit circle. We say that it's hyperbolic if it's conjugate to multiplication by some positive real number, different from 1, right? And we say that it is loxodromic if it has exactly two fixed points and it's not elliptic or hyperbolic. That is, if it's conjugate to multiplication by some complex number, which is not a positive real number and not a circle, right? So that it lies completely outside the union of the circle with the positive part of the real axis. And knowing that here, that in these cases, multiplication by alpha is conjugate with multiplication by alpha inverse, we call both numbers the multipliers of the Möbius transformation. Notice that multiplication by alpha and multiplication by alpha inverse, they are conjugate simply by the Möbius transformation that sends 1 to 1 over z, right? And it's kind of, if you see at the sphere, if you look at the unit sphere, that corresponds to really like a multiplication by alpha. Somehow, instead of looking at it this way, kind of looking at it this way, because recall that z goes to 1 over z, who has a rotation of 180 degrees, right? So it's kind of the fact that multiplication by alpha and by alpha inverse are conjugate somehow amounts to somehow looking at transformations that are very similar and that they only differ by kind of that the behavior of one is the behavior of the other, but rotated. And it's a good exercise to visualize what I just said, but directly on the extended complex plane. Now let us say some words about the conformality of Möbius transformations. This really is just the statement that they are holomorphic as functions from C bar as a Riemann surface to C bar as a Riemann surface. This conformality or this holomorphy, one checks it like, let's say, point by point in C bar. And so when one takes a point in C bar, which is actually in C, and with a property that its image under the Möbius transformation is not infinity, that is, the denominator is not zero, you see one really has kind of around Z naught some neighborhood, right? That kind of where one can where can treat the Möbius transformation simply as a Möbius transformation from a subset of the complex plane to a subset of the complex plane. And when one does that and one computes the derivative, the point is that that derivative satisfies the Cauchy-Riemann equations. And so it is actually a complex differentiable, which can also be seen by here, right? I mean, it's a standard theorem in complex analysis that provided the denominator is not zero, the quotient of two polynomials is holomorphic in the places where the denominator doesn't vanish. Okay, and then it's holomorphic with this as a derivative, right? And somehow the point is that if one wants to see it kind of more in a as a basic differential geometry fact, what one has is a C-linear transformation from the tangent plane to the tangent plane. And that C-linear transformation is given by multiplication by this complex number. And the fact that it's multiplication by this complex number, what it in the end tells us is that whenever I have two curves that two differentiable curves that pass through Z0 in the domain, right? And then I measure the directed angle from one to the other. That angle is equal to the angle formed by the images of the curves under the given holomorphic function, which in this case is mu of A. Right? And that angle is actually measured. Where is it measured? Well, it's measured in the tangent planes. Right? Both of these angles, they are really the angles between the derivatives of the curves, which really are tangent vectors at Z0, right? And they live in the corresponding tangent plane. And their images, when I consider the images of the curves, how do I measure the angle? Well, I take the derivatives of those curves, which are images of the first one, and then I measure the angle in this tangent plane, right? And the angle between tangent vectors. And whenever a function is holomorphic, that is, whenever a function is its derivative, whenever I have a function and its derivative is given as by multiplication by a non-zero complex number, these angles are preserved. Right? Here, kind of angles between vectors are preserved by this linear map, and that's what it means. More formally, more strictly speaking, seeing as a real 2x2 matrix, right? So when I see this, when I compute the matrix of this as a 2x2 matrix, so when I consider this just as a real linear map, that's as an R linear map, that matrix is a positive scalar multiple of an orthogonal matrix. That's what it means to be conformal, and that's the definition of being conformal. And a conformal function always preserves angles, right? Just at the level here, because an orthogonal matrix always preserves, well, the inner product, so it preserves angles, right? And multiplying by and having multiplying by a positive integer, by a positive number, that is having a positive multiple of an orthogonal matrix, well, multiplying by a positive number preserves angles as well. Okay, but so somehow this is the easy case where the point in C bar that I took is actually a complex number, and its image is also its image under the Möbius transformation is also a complex number. And now the kind of the hard part would be to compute the derivative for Z0 equal infinity, or for Z0 with the property that its image under the Möbius transformation is infinity. And this I leave to you, kind of so that you train your, let's say, your differential geometry definitions, so that you practice your differential geometry definitions. And so now we finally move on to Steiner grids. As I've been saying, somehow, you see, now we know that a Möbius transformation, different from the identity, is always conjugate to a standard example. And in the standard examples, it was very easy to provide some basic analysis of the geometric behavior. Right? I mean, we came up with some families of curves right? And then there was always a family, each of whose curves was preserved by all the integral powers of the given standard example. And there was another family of curves which was kind of transversal, and in many cases actually orthogonal to the other family. And in this other family, the Möbius transformation doesn't preserve each member, but rather permutes the members, right? The image of one member is another member. Okay, and now we know we know that conjugating appropriately, we obtain a standard example, right? And then when we apply the inverse of the conjugating transformation, we should be able to pull back these families to give some basic analysis of the geometric behavior of my arbitrary Möbius transformation. And what I know about the conjugating transformation and its inverse is that they are Möbius transformations. So they send circles to circles, and they are conformal. They preserve the oriented angles or directed angles between curves. So if I knew that for the standard examples some families were orthogonal, when I pull through the inverse of the conjugating transformation, I should have orthogonal families. And if I knew that the curves were circles in C bar in the standard examples, I should know that now the images are circles in C bar. Right? So that's why we have been doing all of this, so that now we can transport the geometric analysis from the standard examples to the arbitrary examples. Okay, so now in the parabolic case, so when my Möbius transformation has exactly one fixed point. In that case, I know that nu is conjugate to any translation you want to give me, right? Because I know that it's conjugate to a translation, and I know that any two translations are conjugate. And I know, and for each translation, I have an analysis of the geometric behavior. I want to pull it back, but so I would rather I better make sure that it doesn't matter which translation of which translation I pull the geometric information off. For my nu, I always get the same information, right? And that's what this exercise says. So consider the parabolic transformation, and let's say that it has here some fixed point. And then take a Möbius transformation, let's say tau, that takes this fixed point to infinity. Okay, and then what I have is when I conjugate, the infinity becomes a fixed point. Infinity becomes a fixed point of the conjugation tau nu tau inverse. Right. So tau nu tau inverse is a translation. Let's say translation by some vector beta. Right. But you see, here for tau, I could take any Möbius transformation that sends the fixed point to infinity. So take another one, let's say sigma. Right? If I take another one, let's say sigma, and now infinity becomes, since it's the image under sigma of this fixed point, infinity is the fixed point of sigma nu sigma inverse. And sigma nu sigma inverse is translation by some vector, let's say beta prime. And then somehow I would like that this family of curves that are parallel to beta prime, when I apply sigma inverse to them, I would like that it gives me the same result as applying tau inverse to the family of curves parallel to beta here. I would like these two results to be the same. Right, but that's what the exercise asks. you see, to check that the results are the same, it's enough to check that sigma tau inverse takes these ones to these ones. Right? And then also the orthogonal family to the orthogonal family. Okay, so that's what the exercise asks. And knowing once you do this exercise, which is not very hard, what I see is that then it doesn't matter which tau I use, as long as it sends this fixed point to infinity. So as long as it sends this fixed point to infinity, I can just use it to conjugate, and then once I conjugate, I know that it's this is a translation, so I know it's given by translating by some vector beta, and then I can just apply tau inverse to this, and then what I obtain is a well-defined family of circles in C bar through infinity. Sorry, through the fixed point, because I know that all of these, when they really are circles in C bar that go to infinity. Right? And then actually, like if I continue on the other side, somehow the conceptual picture is something like this. So the images under tau inverse, they have to be circles in C bar that pass through this fixed point. And you see, even since here any two, they share only the point at infinity, these circles, they have to be really tangent at the fixed point. Right? And when I consider the orthogonal family of straight lines, which is, like, again, circles that pass through infinity, here I should have another family, which is, their members, they are again all tangent to each other at the fixed point, and they have to be orthogonal to the members of the first family. Okay, so to the pair consisting of both families, you see tau inverse of the parallel lines to the translating vector, and tau inverse of the orthogonal lines to the translating vector. Right? So these families, I call the pair consisting of them the Steiner grid of my parabolic Möbius transformation. Right? So the final result would look more or less like this, where here I'm thinking that the orange circles are the members of the first family, and so each of the orange circles then is stable on their nu, and that the red circles here, I'm thinking that they are the members of the second family. So actually, nu permutes the family of red circles, right? And this is kind of this is all the behavior is organized in a grid, right? Kind of in this grid that you can see when you consider them at the same time, right? Because, for instance, let's say that I take this point and then I apply tau to it, and let's say that the image is this other point, and now I apply tau to this new point, and then let's say that I end up here, right? And then I end up here when I keep applying tau to the resulting points. So somehow the behavior then one should picture is more or less this, right? That's why this orange circle, that's how the orange circle looks like, being stable under the action of nu. And on the other hand, somehow you see here, this point was not only on that orange circle, but was also in this red circle. And the image of this red circle, then let's say, then it would be like this circle, and then the image of this new circle would be this, and then the image of this new circle would be some circle like this. and so on. Right? And then you see somehow it's kind of the behavior is something like, you see, I started kind of on this side, and then it starts kind of opening, and then it somehow like comes back on the other side and starts to converge to the fixed point on the other side. And that is somehow the behavior, and that behavior is really reminiscent of the fact that, you know, when you take a let's say when you take a line and start translating it by the same vector beta, right? One of these lines are orthogonal to the translating vector. It's kind of, you see, kind of you come from one side close to infinity, and then you start, and then you keep going, and then you move away, and then you go to infinity, to the same point at infinity, but on the other side. So somehow that's why these kind of go opening and then coming back on the other side and closing on the other side. That's why this behavior looks like that. And then somehow, if you wanted to see it on the sphere, so you see somehow the orange circles, you can see them there, and I'm thinking that each orange circle is preserved by all the integral powers of nu. And then let's say I take this circle. No, let's say that I take a smaller one. Let's say one here, right? And then I'm thinking that I'm going to get away from the fixed point on one side, and I'm going to come back on the other. Right? So somehow the image looks, the images of the first circle on their repeated iterations, they kind of look like this, and then let's say at some point, let's say that I hit the one I had drawn at the beginning, and then I keep going, and then, well, it becomes a bit harder to draw, but because my circles look very deformed. And somehow what you are seeing there, you see, it was kind of the behavior of the positive iterations of tau, right? And somehow the flow somehow is along the orange circles, kind of on a grid, it's kind of grid-wise, the behavior, right? So somehow, right? So somehow it's kind of on the orange circles, at least the behavior I drew, it's kind of like this, but it's kind of, it's always kind of all consistent, but not only kind of in direction, but also it's also well organized along the transversal circles. And well, these two families, since we knew that in the standard example, in the translation, what I had was two families of curves that foliate C bar minus the fixed point. Well, I have the corresponding property, but now for my Möbius transformation. And here is some homework. Here are the two exercises to hand in next Wednesday.